The rational root theorem allows us to make a list of all possible rational roots of a polynomial with integer coefficients. And what we're going to do is we're first going to list all of the factors of the constant term. So in standard form, that last number, the constant term, we're going to call all of its integer factors p. And then we're going to look at the leading coefficient, the number in front of the very first term in standard form, and we're going to call all of its integer factors q. And then we list all possible combinations of p over q, and that's a list of potential rational zeros. So let's look at an example. Okay, first I'm going to list all the factors of the constant term, and I call those p. So the factors of 2 are positive or negative 1 and 2. So I do plus or minus 1 and plus or minus 2. And we're always going to have that plus or minus because whether a number is positive or negative, its factors can be positive or negative. Okay, now we list the factors of the leading coefficient, and we call those q. And the leading coefficient is also 2, so its factors are also plus or minus 1 and plus or minus 2. And then I take all possible combinations of p over q. So first, I am going to take the plus or minus 1 for p, put that on top, and I can have plus or minus 1 over plus or minus 1. And I can have plus or minus 1 over plus or minus 2. That gives me plus or minus 1 and plus or minus 1/2. Then I'm going to take the plus or minus 2p value, put it over the plus or minus 1. That gives me plus or minus 2. And then when I do plus or minus 2 over plus or minus 2, it gives me plus or minus 1, which is already in my list. So that's all of the possible combinations of p over q, and I think it's helpful to put them in a table. So x, f of x, and we've got positive 1, negative 1, positive 1/2, negative 1/2, positive 2, and negative 2. And then we could test them all if we want by plugging them all into f of x and seeing if any of them actually give us 0. So any rational roots of this polynomial must be in this list. Now, not all of these numbers are going to be roots, so we're going to test them by plugging them into f of x and see which ones actually give us 0. When I plug 1 into f of x, I get negative 6, so 1 is not a 0 of the polynomial. When I plug negative 1 in, I get 0, so I found a 0 of the polynomial, negative 1. When I plug in 1/2, I get negative 9 over 2. So 1/2 is not a root. When I plug in negative 1/2, I get 0. So I found another 0 of the polynomial. And then when I plug in 2, I also get 0. So there's another root. And since this is a third degree polynomial, I think I just found all of them, because plugging in negative 2 gives me negative 12. So I was actually able to find all the roots or zeros of this polynomial. So if the zeros of this polynomial are negative 1, negative 1/2, and 2, I could find the corresponding factors. And they will be x plus 1, x plus 1/2, and x minus 2. So if I want, I could write this polynomial in factored form. And that would be f of x equals x minus 1, x plus 1/2, x minus 2. This would also allow me to graph the polynomial if I wanted to do that. I know the end behavior of this polynomial. Since my leading term is 2x to the third, I have a positive leading coefficient and an odd degree, so my end behavior is down then up. My zeros, which I just found, are at negative 1, negative 1/2, and positive 2. And I would need my y-intercept, which I find by plugging in x equals 0. When I plug in 0 to this polynomial, I'm going to get negative 2. So the y-intercept would be down here at negative 2. And then following my end behavior, all of my zeros are going to have multiplicity 1. Because the multiplicities need to add up to the degree, and it's degree 3, so they're all going to cross. And so I would start down below, cross, cross, go through my y-intercept, and then cross at 2, and the polynomial would look something like that. Here's one more example. First, I'm going to list all possible factors of negative 18, I call those P. Factors of 18 are going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18. So we're going to have a long list this time. And for Q, this Q is a 1 this time because there's no number in front of x to the third. We just get plus or minus 1. Now, for my possible combinations of P over Q, I've got all those P values, but they can all only be over a plus or minus 1. So basically, my list of possible P values is going to be all possible rational roots. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18 would be all possible rational roots of this polynomial. Now, to test and find out which ones actually are, we plug them in. And I can give you guys some calculator tricks on how to do this a little more quickly, because it's sort of a tedious process. And later in the next example, we'll see that once you find 1 0, you really don't need to find all of them. But if in some of the homework problems, it does tell you to find all of the rational roots. So I'm going to put them in a table. Negative 1, 1, negative 2, 2, negative 3, 3, negative 6, positive 6, negative 9, 9, negative 18, and 18. And then we just plug them all into f of x and see which ones actually give us 0. In the interest of time, I paused the video and found the values you get when you plug in all those different numbers into f of x. And I did find 2 of the numbers in the list that actually gave me 0. So 2 of the zeros of this polynomial are 2 and negative 3. And if I wanted to write this polynomial in factored form, I could use synthetic division to factor the polynomial. Okay, now we're going to see an example where we use the rational root theorem to write a polynomial in factored form. And I want to show how you don't have to test every single potential 0. But first, let's use the rational root theorem to find the potential zeros. So first I take my constant term and I list its factors and call them P. So we get plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6 would be all the factors of negative 6. And then I list the factors of my leading coefficient, which is a 1, so Q is just going to be plus or minus 1. And then when I do all possible combinations of P over Q, all of those P numbers are going to be over plus or minus 1 for Q, so it's just going to be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And now I'm going to make a table where I plug these numbers in. And I'm just going to plug numbers in until I find one that gives me 0. And once I find one, I'm not going to keep plugging numbers in because it's tedious, and I really only need one, and then I can use synthetic division and factoring to go from there. Okay, first I'm going to plug in -1. And when I plug in -1, I get -4. So that's not a root of the polynomial. Then I try plugging in 1. When I plug in 1, I do get 0. So I found one. 1 is a 0 of the polynomial. Now I'm not going to keep going and find others. Instead, I'm going to use synthetic division. So remember, my goal is to find the zeros in the factors. And I know that 1 is a 0, and that means that x minus 1 is one of the factors. So if my goal is to write this in factored form, I already know that I can start with f of x equals x minus 1 times something else. I don't know what. But if I use synthetic division, I can figure out what that would be. So I'm going to take my original f of x and divide it by x minus 1 using synthetic division. And to do that, I put the 0, 1 in the little corner. I list the coefficients of f of x, which are, it's 1x cubed, so I put a 1. 4x squared, I put a 4. 1x, so I put a 1, and then minus 6. I put a vertical line between my last two numbers, a horizontal line, leaving space for another row of numbers. I bring that 1 below the line, and then I multiply the 1 in the corner by the 1 below, and we get 1. Add the 4 plus the 1, we get 5. 1 times 5 is 5. 1 plus 5 is 6. 1 times 6 is 6. -6 plus 6 is 0. That's my remainder, my constant, my x, and my x squared. So f of x divided by x minus 1 is 1x squared plus 5x plus 6. And the fact that we got 0 as a remainder reinforces the idea that 1 is a 0 of the polynomial, and x minus 1 is a factor. So in factored form, x minus 1 times x squared plus 5x plus 6. And now we can continue to factor using our factoring skills, because we're down to, when we divided a third degree polynomial by a linear factor, we got down to a second degree polynomial quadratic, which we know how to factor. So I leave that x minus 1, and I factor x squared plus 5x plus 6 into two binomials, and that's going to be x plus 2 and x plus 3. And so now I can write f of x in fully factored form. And I also know I can find all of the zeros of the polynomial now. So since x minus 1 is a factor, 1 is a 0, x plus 2 is a factor, -2 is a 0, x plus 3 is a factor, -3 is a 0. So the zeros of the polynomial are 1, -2, and -3. Those are also the solutions, or the x-intercepts of the polynomial. In this case, this polynomial had 3 real zeros and no complex zeros. And here's one final example. First, we're going to use the rational root theorem. But actually, before we do that, to factor this polynomial, we can, just by looking at it, there is a GCF of x. So I can factor x out of the polynomial and begin to write this polynomial in factored form. So we get f of x equals x times x to the 4th plus 3x squared minus 4. And now the polynomial that I'm going to do the rational root theorem for is going to be this one inside here because I've already factored out that x. So I'm going to look at the constant term at the end, the -4, that's going to be my p, and the factors of p are, or of -4, are going to be plus or minus 1, plus or minus 2, and plus or minus 4. Q is going to be the integer factors of 1, the leading coefficient. So Q in this case is plus or minus 1. And all of our P over Q combinations are going to be plus or minus 1, plus or minus 2, and plus or minus 4. So I'm going to test them until I find one that works. So we get x, f of x, -1, +1, -2, +2, -4, and +4. Remember, these are just potential zeros, and we're going to test a few until we find one that's actually a 0. When I plug -1 into f of x, I actually get 0 right off the bat, so I already found one. So if I make a list of my zeros and factors, -1 is a 0, so x plus 1 must be a factor. So if I continue to write this in factored form, I already know that I factored out an x in the beginning. I'm also going to have an x plus 1, and I'm not sure what else. So I'm going to use polynomial or synthetic division to divide my polynomial x to the 4th plus 3x squared minus 4 by x plus 1. So I put the 0 in the corner, -1. I list the coefficients of x to the 4th plus 3x squared minus 4, and the coefficient of x to the 4th is 1. Now I'm missing an x to the 3rd term, so I need to put a 0 to hold that place. And then I do have an x squared term, it's a 3. I don't have an x term, so I need to put another 0, and then -4 is my constant. Vertical line between my last two numbers, a horizontal line, leaving space for another row of numbers. Bring the 1 below the line. And we multiply. -1 times 1 is -1. Add 0 plus -1 is -1. Multiply -1 times -1, we get +1. Add 3 plus 1, we get 4. Multiply -1 times 4, we get -4. Add 0 plus -4 is -4. Multiply -1 times -4, we get +4. Add, we get 0. If we didn't get 0, we would have a problem because we already found that -1 was a 0, so the remainder better be 0. And that confirms that it is. And then the constant is -4. The x term is 4, has a coefficient of 4. X squared has a coefficient of -1, and x to the 3rd has a coefficient of 1. So that is still not going to be enough to factor this, because if I go ahead and put that in my missing place here, so we've got 1x to the 3rd minus x squared plus x minus 4. I still don't know how to factor that, so I do need to find another 0. Sometimes zeros can work twice, so we could try -1 and see if it works again, like maybe it has multiplicity 2. And we don't need to completely start over. We can take that list of numbers that we just got and make a new line between its last two numbers and a new line below. And let's try -1 again and see if it happens to be a root that has multiplicity greater than 1. So I'm going to try synthetic division again and just see what happens. I move the 1 below the line. I do my synthetic division, positive 1. I multiply, add, multiply, add, multiply, and add. And I didn't get 0, so that means negative 1 is not a double root. So I'm going to go ahead and erase that because it didn't work. And I'm going to go back to my list of P's and Q's and see if I can find one that does, another one that works. Okay, when I plugged 1 into f of x, I actually got 0 again. So I got lucky because my first two numbers in my table were both zeros. So now I'm going to add 1 to my list of zeros, and that means x minus 1 must be a factor. So continuing to write this in factored form, now I have x plus 1, and x minus 1. And I'm going to do synthetic division again, and after I do that, when I do a third degree divided by a linear, I'm going to get a quadratic, a second degree. So I should be able to factor from there if it's factorable. So now I'm going to do that synthetic division with a positive 1 in the corner. I bring the 1 below the line. I multiply, add, multiply, add, multiply, add. And I did get a remainder of 0, which confirms that 1 is a 0 of the polynomial. And then my answer, my remainder is 0, my constant is 4, there's no x term, and my coefficient of x squared is a 1. So this represents x squared plus 4. So I'm going to pop that into factored form. And I asked myself, can I factor that more? But I cannot factor a sum of two perfect squares. It's not factorable. So now this is actually fully factored. So the zeros of this polynomial, well, I have 3 real zeros. I have a 0, the x gives us 0, x plus 1 gives us negative 1 as a 0, x minus 1 gives us positive 1 as a 0, and then if I solve x squared plus 4 equals 0, x squared equals negative 4, square root both sides, plus or minus, x equals plus or minus 2i. So positive 2i and negative 2i are the other two zeros. So that's all zeros of this polynomial. Remember, it was degree 5, and the number of zeros should add up to the degree, and it does. In this case, we had 3 real zeros and 2 imaginary zeros. And if you wanted to, you could graph this polynomial too. But for now, we're just solving.